hope it's audible everywhere properly. And yeah, of course, he mentioned quite a lot of words. I hope the aim of this presentation is at least you understand two of those words. So let's see how it goes. And I hope you guys are not sleepy after the good lunch. So yeah, let's start us. So the title, as you can see, is Near Zero Defects. It's basically where we talk about visual anomaly detection on edge devices. And this is given by me and my colleague. I'm Rajesh. Ashwin. So yeah, well, it's probably not audible. He's Ashwin. We both work as AI researchers at a team we call Getty Labs at Intel. So yeah, let's get started, right? So a quick question is before I start even with the outline, how many of you have heard of anomaly detection before? Okay, easy audience. So in this, what we try to do is in the next 25 minutes, talk you through some of the concepts of anomaly detection, some of the challenges that we face in anomaly detection, and that's basically like the theory stuff. And then Ashwin will present how we solve this and how we do this using our open source libraries. And at the end, we also talk about how we can do all of this not on like a huge server rack, but on a very thin, nice, small CPU on device. So yeah, let's get started. Well, I think most of you raised hand for when asked what is anomaly detection, and I think most of you already know it. So in a very broad way, anomaly detection is basically uh, well, in a very simple way, it's just finding what is not normal, and it's and what you define as normal is basically is up to you. For example, if you take a small example, right? So in this, it's a yeah on the right side are the images of good PCB with the green boxes, and I can define those to be normal, which means normally they are assembled all at in a proper way. There's no defects, at least visually. It's not there's no like electrically working this thing, but it's visually all looking good. And on the other side, I can see that there are some defects. For example, there's on the first one there's like a bent pin. On the other one there's like a like a not so good soldering thing for the IC. So these I would say as like anomaly, right? So now it is clear what we define as normal and what we define as anomaly. And sometimes what happens is this is pretty clear. Sometimes it depends really on the context. For example, if you have another industry which is making juice bottles, I assume. In this case, what do you consider as normal? Do you think the stickers that are printed in reverse order would that make as a anomaly, or would it just be like it's fine, up to you? So there are two types of anomalies. So previously I showed, right, it's a proper anomaly, and there's this logical anomalies. And if you want to be like I also want to detect logical anomalies, one way is to think that your normal set of images has only the images which have stickers in particular format, and then you can say that the other ones are anomaly. But otherwise, if you treat all the four of these as normal images, then your anomaly is a entirely different thing. So how does it differ from classification? In pretty simple thing, classification, let's say an easy example, we have two classes, and you know both the classes, you have images from both classes. And in classification, what we essentially try to do is try to understand this boundary between the two classes, where which says like everything on the other side of boundaries, a class A, and the other side is class B. But the problem with anomaly detection is it's in a way unbounded by nature. That one thing is, you know what is normal. Most of the times you only have normal images, and the second thing is you don't know the anomalous, what is the range of anomalies. So it could be like a bent pin, it could be a broken PCB, it could be a broken soldering. So as I say, it's anomalies are like unknown unknowns. You don't even know what type of anomalies you face until you face them. So in anomaly detection, what we try to do is we try to get the best out of the images, the good images as we call it, as much as possible from them. So we try to have learn this distribution from normal images, and we say that everything around or everything outside this distribution is anomalous. And how do we do this? So how do we go from using a set of normal images and using a model and then somehow be able to detect anomalies? So somehow be able to differentiate between a good and a bad image, and while doing so, also show the localization or the area where the anomaly is happening. So how do we do this? I'll give a very simple example. This is like a very simplest theoretical model. These are most of the distribution or memory based models work. And what we do is, like in is very simple this thing. So we take a set of normal images. Remember that we still have no input from anomaly or anomalous images. We just take normal images. We take a pre-trained model. Could be anything. Could be a wide ResNet. Could be any pre-trained CNN. Could be even Dino V2s. So it could be any model, and we extract the features from it. And once we extract the features, what we do is we try to learn a distribution of these normal images. Could be a Gaussian distribution, could be a entirely different things, but we try to learn the distribution, the bounds of this. So what happens is once you have this, when you have a anomalous image or during test time in general, either a normal or a anomalous image, we use the same model and we use the same process where we extract the features, and then we try to see how far it is from this learned distribution from our training phase. So for example, how do we know how far it is? We can just do as simple as Euclidean distance. We can do things like cosine similarity. We can do a lot of things, but this is how more or less how we see how if an image is anomalous or normal, and we basically put a threshold, seeing that yeah, if it's further than yeah so and so number, it is anomaly, or otherwise it's a normal image. And again, just a reminder, all this just by using normal images for training. And then the question is, and the example I was showing, right? There was a part which was very bright red, which indicated that yeah, there was some problem, there was some anomaly at that area. How do we do that? We do that basically using the same concept. What we do is instead of doing at an image level, we divide the image into multiple patches. I mean here it's just 9 by 9, but in theory it could be like yeah very like 16 cross 16 or yeah as many patches. And then for each patch, for example, for a left corner of the image we learn a distribution, for a right corner we learn one distribution, so for each patch we learn a distribution. And then what happens is we do the same thing during inference as well. We just for any input image, we do the same thing. We do patches and see across all the patches if there is some anomaly, and then based on that we can apply some logic on that to determine if the whole image is anomaly or not. And also the region that made the patch that made it anomaly will be yeah basically highlighted. Of course this is in a very simplest way, and of course the research is now much growing. It's not as famous as let's say object detection or even like the recent LLM stuff, but anomaly detection has been there for yeah quite a long time. It's been used in industries all across to detect anomalies and basically to reduce yeah well failures. And there are quite a lot of models, and this is again a very small subset in the Anomalib library that we work on, which is an open source library. We have I think close to 20-ish models or 20 plus models, and they are all of different types. So let's take a look at maybe one or two of them and see, just to give a good idea of how other anomaly detection methods work as well. So for example, this is called as a teacher-student model. And what happens is during the training, again, the same story. We train using only normal images. During the training, what happens is we take this pre-trained teacher model, and it is never, well, there's no gradient propagation in that. It's only used for feature extraction and feature map extraction. And we use a student model, which is having basically the same architecture as teacher model or slightly smaller one. And then what we do is we try to make this student model learn to predict the feature maps of the same thing that the teacher model is doing. So in a way, student learns. The student model is trying to understand the same feature maps. Like for example, if I give image A, the feature map that the teacher model gives, the student model will try to learn to generate the same thing. And the loss function objective is to, yeah, basically try to learn it as much as possible. So in a way, what happens is now the student model has learned only on normal images. So when an anomalous image comes, what happens is it will not be able to create the same feature map that the teacher has created. And when you just take the difference between them, you get whether it's an anomaly or not. So that's a very simple way of telling this teacher student model. And there's now some new ways of doing anomaly detection, maybe not the best suited for industrial ones. I'll come why this is. And this is a paper from like 2 years back, which is called WinClip. And as the name indicates, it uses these foundation models like Clip, basically. And instead of just relying on image embeddings, what it does is it also uses text embeddings. So as yeah, what we do, at least in our library, is we give a set of well, basically prompts, which are like which correspond to both normal and anomalous images. So what we say is, yeah, this is a photo of a yeah, let's say PCB, and it's all good. Or we say that this is a photo of a good transistor without any defects. And at the same time, we also have a set of prompts for the bad image. So where we say that, yeah, this is a image of a PCB with, yeah, some bent wire or some soldering issue. So now what happens is we then compare the image features with the text prompts, and Clip is a joint embedding space, right? So it does that. We do this comparison, and then we see if there's a difference between the image embedding and the text embedding. So if the difference is huge, then we can say that, yeah, it could be an anomaly. And what we also do is this is all zero shot. There's also like a single shot thing where you can give one image as a reference and say that this is a good image, and treat this image as a standard for the next, yeah, for this activity. And then whenever there's another image which is, yeah, slightly anomalous, you can see that, yeah, there'll be a huge difference for this. So this is more or less theory. I hope the boring part is more or less over. Uh, the one which I like is the challenges. It's still an ongoing thing. People are still every year, like at CVPR and ECCV, we still have like so many papers which are trying to come up with solutions for these challenges. And the main challenges in anomaly detection, unlike for all other ones, is you don't really have your anomalous images unless you find them. So usually people start with yeah, normal images, and the problem with normal images is no matter how many you collect, after like 100 images, they are more or less going to look same. So that's what it says. Like all positive examples are alike, but each negative example is negative in its own way. Like you don't know, you can face a bent wire, you can face like a soldering issue, or you can feel that there's an entire component missing from it. So what happens now is, because of this particular scenario, we have this challenge where, yeah, there is a constant research evolving around what metrics to use, how do we determine the threshold, and how do we determine this normalization. And let's quickly look into one of them. So this is what I was saying, right? So in a real life, in a practical scenario, like in research, of course, you have all your good test sets and all your training data sets, good and bad examples. But in real scenarios, you will have like what, 30, 40, 100 images which are good, but you'll have like maybe three of, or even zero abnormal images. So in an industrial scenario, how do we acquire this anomalous image? That is still a very big open question. And the problem with this, if you treat it as a class imbalance, is basically we get all the problems of, well, imbalanced data set, right? If my anomaly detection, if I say my anomaly detection model has an accuracy of, let's say, 99 or even 100%, you can't still trust it, because it can just say that, yeah, every image that it sees is a normal image. So your accuracy will probably be still high for normal images, but it won't work for imbalanced data set. And the same thing happens when there is at the pixel level as well. So for example, in this one, the green part I hope it is still looking as green. So the green part is the anomalous area, the ground truth, let's say. And if your model detects that the red part is what is anomalous, technically it's true. You'll get a very high precision as well because whatever it detected as anomaly is actually anomaly. But then if you just blindly follow high precision models, it's going to miss a lot of the anomalous area. And the same thing happens with recall as well. So like my model can just say that, yeah, everything that I see is anomaly. And yeah, you get a high recall, but you'll have also like super high false positives, and you can't just discard every other transistor that you see as an anomaly. And so mostly what happens is we try to use none of this. We try to use a combination of this through F1, and I think everyone here knows what how F1 is measured. So it's a bit of mix of both precision and recall. You need both of them. And apart from this, there are also like some metrics like uh, people have started to use more things like true positive rate at 5% false positives. So that means you can let's say if you have 100 images and if you say that if your model is tuned to detect 95% of them as correctly as normal, and that at that threshold how many anomalous images can it detect, that's the rate. So it's a bit complicated. It's a very specific to the use case that you use, but in general, yeah, instead of precision recall, F1 is mostly the score that most papers hopefully report as well. And then there is this next problem, which is threshold selection. So you know your normal images, and that forms a nice, let's say, distribution like in the blue one. And the problem is the red one that I'm showing, the red distribution here, can, or like let's say you won't know what it is because you don't. If you have zero anomalous images, then you will never know what it is. And even if you have three anomalous images, then yeah, you will still be like, yeah, you'll have an incomplete distribution. You don't know what is the trend really there. So a naive way to do is how we select threshold is, let's say we can select something. Let's hope if this works. So yeah, I can just say something like around. Okay, my mouse is not working, but yeah, something around 90, like 6 sigma or something. And if you assume your normal distribution, you can just say 6 sigma. That's a very industry standard, right? So you assume that your 99 point, I think 997% of all the normal images get, yeah, classified correctly. But then yeah, but then the thing is you won't know if your anomalous distribution, is it overlapping, is it overlapping halfway, or is it overlapping entirely. In that case it's useless. So that is just still naive. And then the third problem I want to talk is normalization, right? So like unlike classification models which just give a, which they have a sigmoid function or like a other activation functions which just tell, which put the number between 0 to 1, right? It says, yeah, this yeah, well, this belongs to class A with 60% confidence or 70% confidence. But with anomaly detection, what happens is you can't do it. You can't do it because you don't know what is anomaly scores and the range of anomaly scores. So it could be as much as yeah, 0 to 10. It depends entirely on model. It could be 0 to 100. So the problem is you can't really do this normalization unless you know some samples from OOD dataset. And even if you have that, OOD is out of distribution detection. And even if you have some anomalous samples, the thing is you might want to clip the models, right? You might want to clip the range. That is, let's say if you have three images and they three anomalous images and each of them give a score of, yeah, 20, 30, and 40 anomalous score. Do you clip it at 40? Do you clip it at 50? Do you clip it at 100? Are you sure that there won't be any stronger anomalous images later on? So that's the whole point of anomaly detection, that the it looks like most of our problems will be solved if only we had anomalous images to solve, anomalous images to do all this, right? And luckily there is some research around this. I think this is one of the fancy word that was mentioned. So synthetic anomaly generation, and that's like you take a normal image, and a simplest way to do it is apply Perlin noise, which is quite random, and then apply a random texture on that as well. And for textures, I think some of you might know DTD dataset, which is just a which has things like spiral or just webbed or things like that, those patterns. So you take this Berlin noise, add this texture, and then use it on normal images. And suddenly, what you have is, let's say if you have 100 normal images, and previously you have 0 anomalous images, and now suddenly you have, yeah, you can apply it on all the normal images and get anomalous images. So yeah, if you have 60 normal images, now you have 60 anomalous images as well. So this, I hope, was not boring, but this is the least boring part of it. Ashwin will tell you more in the next few minutes about how we do it from in terms of in practice using Anomalib. So
Thanks. So that was a major part, the heavy lifting of all the concept behind it. But what's nice is luckily we consolidated everything, put it in open source library called Anomalib, and wrong direction. But if you want to know more, we gave a talk about it like 2 years ago, so we're not going to go in detail. But what we have is a theme data set we're going to quickly show a demo on. And we have a lot of good images and a few bad images. And we'll quickly show you how can you train just in 3 lines. So you can basically just import a model. So you're going to use PatchCore, which is very famous, and it's one of the clustering-based models. And you can basically point to your data set. You can say, hey, these are where the good images are, these are where the bad images are. And what it does in the first example, it actually uses one anomalous sample to calculate threshold. And in the second example, you just remove abnormal, point to and say, hey, I want to generate the validation split using synthetic data. And that's the result you get. We got lucky because when we tried it with this data set, we got better results with synthetic anomaly, which is nice. But internally, we are using the same thing. We're using Berlin noise. And it's because we get more information, more anomalous images. So it's you get a better idea of what is out of distribution for this particular data set. But this is nice. This is nice if you are data scientist, if you want to actually do git clone and all of that. But what we have been working on is actually another open source tool called Git Inspect, and we're going to quickly switch to demo, and which is actually on the feature branch. So it will be out soon. But I mean, if you guys want to try it, you can. It's cutting edge, so stuff will break. And it's even more cutting edge because Mark has been like editing it right now while we have so but you'll have to clearly so all right, so I'm just going to create a project quickly, and that's convenient. I have a project already ready. So unfortunately, what I did is I just took 13 images, and your team decided we're going to have minimum 20 images, and all temporary solutions are permanent. So here we are, and so these are all the models we exposed from Anomaly. We're going to make it, clean it up, but I'm quickly going to start training PatchCore. And the idea is, okay, you have all this, you have data engineers who make all of this, but how do you apply it in practice? And idea is, okay, we can go now to Foundry or anyone. We can give this tool. We can be like, hey, you know what? Upload your data, maybe annotate stuff. You can select the model. You can play around with it. And later on, what you can do is then be like, hey, you know what? I want to connect the camera attached to this factory floor, and I want to say send the output to some MQTT buffer or a webhook or just some ROS model. And what you see here is it's trained. In the background, basically, it's just picked up it learns the distribution by. We can talk about it in detail. I mean, there's a really cool stuff which it does, and it's even this model it holds out really well, and of course it's broken, but you should to just refresh or yeah, all right, and. Cutting edge, yeah. You're on the bleeding edge. And now you can see the results. Not perfect, but did work really well. The fact that we didn't give any anomalous image. And yeah, this is nice. For sake of time, I'm not going to switch again. But main thing is, how do you do this? How do you run this in industry, right? You train it, you can use beefy GPUs, everything, but they're expensive. Then you need, heat is a main problem. You have issues with dust and all. But ideally, when you want to run on, when you have a trained model, you can run it on, like on device, on a small machine like this, smaller machine like this, like those small and this Intel NPU, whatever. And if you guys attended Mark's talk, the thing is, what you can do is you can export the graph. And what we do is we embed both pre-processing and post-processing in the graph. So even your resizing operation, and also just this thresholding, normalization, everything is in the graph. Because the backend themselves, like Onyx and OpenVINO by Intel, they're written in C++, right? So you get that basically native performance. And those things you can deploy on a more memory efficient and a hardware which uses lesser watts and all. And yeah, I'll show you the graph later on maybe, but you get twice the performance speed compared to this. But I'm going to open to question, and yeah, feel free.
Perfect. Thank you so much. Please give them applause.